In this video, I'm going to illustrate how to carry out bootstrapping using the AMOS program, and this is going to be done in the context of testing a path analysis model. The basic principles that you see in this video can be extended to other structural equation model other structural equation models, such as CFA models and path analysis models with latent variables. So bootstrapping can be useful in those cases where your data fail to exhibit multivariate normality, which is an assumption associated with maximum likelihood estimation. That estimation approach is the default in many SEM programs. So when your data do not meet the assumption of multivariate normality, then estimations using maximum likelihood can yield inflated chi-square values, leading you to conclude that your model is a poor fit to the data. And it can also decrease the size of the standard errors for the parameters in your model, which can yield increased type 1 error rates. So basically we can utilize bootstrapping to sort of offset some of those problems. And so I'm going to illustrate some of those procedures here. In addition, even if it happens to be the case that your observed variables in your model do exhibit multivariate normality and meet the assumption of maximum likelihood estimation, it's still also the case that in AMOS there are no significance tests associated with tests of indirect effects. And so that's problematic if you want to test whether the indirect effect of one variable on another variable is statistically significant. So one way around that problem is to utilize bootstrapping in order to generate standard errors and confidence intervals that can be useful in testing statistical significance for those effects. So here I have a basic path model, and I am going to perform bootstrapping using AMOS. So for argument's sake, let's pretend like I have reason to suspect that that these variables right here fail to exhibit multivariate normal distribution, and I want to test whether the model is a good fit to the data. Ordinarily, if I was going to test model fit, what I would do is I would go under analysis properties, and under estimation I would the default maximum likelihood estimation is already clicked, and I would then go to output and just ask for some standard outputs. I can ask for standardized estimates, squared multiple correlations, indirect effects, test of normality, those sorts of things. And so what I would do is I would basically click on analysis or calculate estimates, and then when I go under the output, I would click on model fit. I would be looking at the chi-square test here to see if this is statistically significant. If it is, that would be one indication that my model is fitting the data poorly. Statistical significance is actually a bad thing when it comes to testing a preferred theoretical model. Bad in the sense that I would end up rejecting the model that I was testing and concluding that it is a poor fit to the data. I'd also be looking at the CFI, the Tucker-Lewis, and root mean square error of approximation, and some other indices to judge the overall fit of the model to the data. Furthermore, I would click on estimates, and as you can see right here, we've got unstandardized regression weights. These would be the unstandardized path coefficients in the model. You would have your standard errors and critical values. These are basically z-values, just formed by dividing the estimate divided by its associated standard error. And then you'd have a p-value associated with those parameters. And so these are the unstandardized path coefficients right here, and their associated tests of significance. You've got the standardized path coefficients here with no significance tests associated with it. and then down below we've got the squared multiple correlations, and when you scroll down even further, you've got total effects, both unstandardized and standardized, direct effects in the model, both unstandardized and standardized, and then the indirect effects, both unstandardized and standardized. But you can see that you have no significance tests for the total effects and the indirect effects. The direct effects are actually going to be the same values that we have up here for these parameters in the model. So now let's look at utilizing bootstrapping and assume that we have a lack of multivariate normality for our observed variables in the model. So what I can do is I can click on Analysis Properties and go to Bootstrap, so under this tab right here. Keep in mind that to perform bootstrapping, it actually requires a couple of things. First of all, you need a complete data set, and you need the raw data. So you can't perform bootstrapping using summary data or matrix summary data. So I'm going to click right here and just kind of show you that I'm going to go to View Data, and this is the data file that we're working from. So it's an SPSS file. These are our variables, and each row constitutes a different case with a person's responses to questionnaire item to subscales on a questionnaire. But this this data set has to be complete. So if there's any missing data whatsoever in your original data set, you're going to have to deal with that prior to carrying out bootstrapping. So whether you decide on a deletion approach like list-wise deletion, or whether you decide on some type of imputation approach, the end result must be that you have a complete data set with no missing values on your variables. So at this point, we have a complete data set. So again, I'm going to go to Analysis Properties. And also, keep in mind that when there's missing data, you have to click on this if you're going to use the full information maximum likelihood approach to estimating model parameters. But this cannot be clicked if you're going to be performing bootstrapping, and that also means that you would have a complete data set to work from. So at any rate, I am now going to click on Bootstrap, and then I'm going to click on Perform Bootstrap. The default in AMOS is 200 bootstrap samples. I'm going to raise it to 500. And to perform the Bollen-Stine bootstrap, which is useful for evaluating the overall fit of your model to the data, I'm going to click on this. Ordinarily, I would also be asking for bias-corrected confidence intervals for the individual parameters in the model, but if I click on that and have this Bollen-Stine bootstrap clicked, then I won't get those confidence intervals. So actually, I'm going to have to run this twice in order to get both the test for overall model fit and then to test the individual parameters in the model. So the Bollen-Stine bootstrap is basically going to be used to assess overall fit, pretty much like what we do with the chi-square goodness of fit tests. So I'm going to click on that, and now I'm going to go to Calculate Estimates. And so you can see it says the chi-square, the maximum likelihood chi-square, which is the default estimation, is 52.8. We've generated 500 bootstrap samples, and now I'm going to go to the view text and take a look at this. And in fact, I think I already have it over here. So you'll notice that in terms of the chi-square value, that's what we had originally. And now I'm going to click on I'll just show you the bootstrap distributions. And basically with bootstrapping, what happens is that a random sample of the original size is taken from your sample data. Your sample data is basically being treated as a pseudo population. We're taking random samples of size n from that pseudo population, and the sampling is with replacement, by the way, and calculating in this case, the chi-square values for each of those samples. So we're going to have 500 chi-square values associated with each sample that is drawn from your sample data. And so you can see that we now have a sampling distribution of the chi-square values, and then so we're looking to see where the chi-square value from the original um, data falls relative to these bootstrap samples. So at any rate, the chi-square from our sample data is 52.847, and you can see right here that 52.847 is going to fall up here in the upper tail of the sampling distribution. So basically, that's actually going to be, visually you can see that that's indicating that our sample data is, our model is not fitting our data particularly well. So I'm going to click on Bollen-Stine Bootstrap, and so in order to evaluate whether or not our model is fitting the data, we really just need to look at this little row right here. And it says it's testing the null hypothesis that the model is correct. So basically, under the null, what we would expect, if the null is correct, we would expect that the p-value associated with our sample data would be greater than 0.05. So that's how we typically assess model fit using the chi-square test. So if our p-value associated with a chi-square test is greater than 0.05, that would be consistent with a good fitting model. If it's less than 0.05, then that would be actually indicating that our model is a poor fit to the data. So you can see that given that we have a p-value equal to 0.002, basically what that's basically telling us is that our model is a poor fit to the data. So just as a little bit of a rehash, if our p-value is less than 0.05, then that's for the Bollen-Stine, that would indicate that we have poor model fit to the data. If it's greater than 0.05, then that would indicate that we have at least acceptable fit to the data. So in this case, we basically are going to reject our model and conclude that it exhibits poor fit to the data. Nevertheless, if I want to go back and evaluate the individual model parameters for statistical significance, then I'll go back to Analysis Properties, and I'll click off of this and click on to Bias Corrected Confidence Intervals. And the default confidence interval in AMOS is 90 for 90% confidence interval. I'm going to set this at 95% confidence interval, and click the little X here, and now I'll click on Calculate Estimates. Go back to View Text, and under Estimates, now when I'll double click, and so you can see these are all the same estimates that we had previously. Earlier when I was just showing you, the significance test, the conventional significance test associated with our path coefficients, the standardized estimates, and so forth. But now down here you'll notice it says estimates, bootstrap standard errors, bootstrap confidence intervals. So if I want to use the bootstrap results, then what I can do is I can click on scalars, and so you can see it's still not highlighted. If I double click on this, now when I click on regression weights, I get the original regression weights or path coefficients that we had previously with the conventional tests of significance. And in fact, these are the results from the conventional tests of significance that we described earlier. If I click on bootstrap standard errors, these are standard errors that can be used in order to test for statistical significance for these parameter estimates. So you can see these are the original standard errors that are computed under our assumptions of normality. And when we click on bootstrap standard errors, these are standard errors that have been adjusted, and they're adjusted using the bootstrap procedure. So when I click on bootstrap confidence, then down below I've got the original estimates that I was just showing you, and now we've got 95% confidence intervals. So I've got the 95% confidence interval between this variable and this variable. So just to kind of give us a visual of what I'm talking about, it's this path right here. The original coefficient, or the estimate, is -0.002. The 95% confidence interval using the bootstrapping procedure is between -0.137 and 0.129. The 95% confidence interval around the estimate from SDO to this variable here, this path right here, that estimate for that path was 0.452. This is the unstandardized estimate, and the confidence interval ranges between 0.23 and 0.641. So in evaluating the statistical significance of an estimate, we can approach it one of two ways. We can either look at the 95% confidence interval and determine if 0 falls within that interval, and 0 is the null hypothesis, meaning that there's no predictive relationship between our predictor and our outcome variable for that particular relationship. So if 0 falls within the interval, then we would judge this to be non-significant. So for this first path right here, 0 falls within the lower and upper bound of our 95% confidence interval of -0.137 and 0.129. So that coefficient right here would be deemed not statistically significant because 0 falls within that bound. On the other hand, if we look at if we're trying to determine if this estimate is statistically significant, when we look at the 95% confidence interval, it ranges between 0.230 and 0.641. 0 obviously falls below the lower bound of this interval, so we would then interpret our estimate to be statistically significant. So we would infer that there is a non-zero predictive relationship between this variable and this variable. So we can either use the 95% confidence interval and basically interpret this the same way we would a confidence interval in the context of multiple regression, or we could just look at the p-value that is listed right here and basically determine if that coefficient is statistically significant. So here we could say that for this first estimate here, the p-value is greater than 0.05, which is our conventional threshold for statistical significance. So this path would be non-significant. Down here you can see that the p-value is well less than 0.05, and so we would deem this estimate to be statistically significant, or this predictive relationship to be statistically significant. The same would go for this predictive relationship here. So you can go either way. So at any rate, these are confidence intervals that are formed and used in order to assess the statistical significance of the individual path coefficients within the model. If we also can click on standardized regression weights, and we get basically these values right here would be interpreted along the same lines as a beta weight in multiple regression, and we have confidence intervals, bootstrapped intervals that are formed around these estimates. So if you wanted to judge the statistical significance associated with the standardized weights, you can do the same thing that we just did with the unstandardized weights. You can also see we've got bootstrapped confidence intervals and standard errors associated with the covariances among the exogenous predictor variables, the correlations, even the squared multiple correlations. So you can see that we have, like for our outcome variable here, the R-square value is 0.301. So in other words, we account for about 30.1% of the variation in this outcome variable here. The bootstrap confidence interval ranges between 0.167 and 0.420. We basically determine if 0 falls within that interval. If it does, then we would say that this estimate is not statistically significant. If 0 falls outside of that bound, then we would deem that R-square value to be statistically significant. Or we can just consult the p-value that's given over here and interpret statistical significance in the same way we've done above. If we click on matrices, you'll see here that these are our total effects, direct effects, and indirect effects. If we, you can see that this is not highlighted, but when we double click on this, we can go to a specific effect that we want to, and then look at the bootstrap standard errors and confidence intervals. So I'm going to click on indirect effects, and so these are the indirect effects. So SDO to this outcome variable here, the indirect effect would actually be going from, there's actually several ways in which the effect of this variable on this variable can occur. We can have mediation through contact directly, so there's one path. We can also have another indirect effect going through contact to predge to opposition. We can also have SDO to predge to opposition. So there are three ways in which the effect of this variable on this variable may be mediated, or the effect would be deemed indirect. So if I want the unstandardized indirect effect, that's what this is right here. The standardized indirect effect is can be found right here. So again, there's the unstandardized indirect effect and the standardized indirect effect. If we want to test the indirect effect for statistical significance, first of all, just again, I want to note that if we click down here, we can get the bootstrap standard errors associated with the indirect effect that was computed. And if we want to test for statistical significance, we now have, again, the 95% confidence intervals for our indirect effect. The lower bound, you can see the lower bound for the indirect effect of SDO on opposition is 0.083. The upper bound for that 95% confidence interval is 0.322, and we ask, does 0 fall between 0.083 and 0.322? Obviously it doesn't, so we would deem that indirect effect, when we go back to estimates, we would deem the indirect effect of this variable on this variable to be statistically significant. We could also, instead of going through that, we could just kind of look at the p-value that's given down below. So these are p-values for these effects. So the p-value is 0.006, which is less than the conventional 0.05 level. So if we wanted to use this approach, we would deem this effect to be statistically significant. If we want to look, let's see another indirect effect. We can look at the effect of this variable on this variable. So the effect of this variable on this variable can flow through contact, and it can also flow through predge to contact to predge to opposition. So when we look at the unstandardized indirect effect, you can see that it is 0. And so when I look at the significance, the 95% confidence interval ranges between a lower bound of negative 0.015 and an upper bound of 0.017. 0 falls between those two points. So that estimate, basically we would deem the relationship between this variable and opposition to be non-significant, and basically the p-value that's given right here, basically it would be 1. If we want to look at the standardized effects, we would still go about the same process of testing for statistical significance there. Keep in mind that when you look at this path diagram, these are the direct effects. The arrows represent the direct effect of one variable on another. Then you have the indirect effect, which is the effect of one variable on another variable flowing through intervening or mediating variables. So again, for this variable on this variable, we've got a path from this variable to contact to opposition, this variable to contact to prejudice to opposition. So that would be the indirect effect. One of the downsides in AMOS is that we can't untangle or disentangle the unique indirect effects. So we can't disentangle the mediation through contact directly from the effect of the mediated effect flowing through contact to this variable to this outcome variable. So the indirect effect is sort of overall effect or an overall indirect effect of one variable on another variable. And then just keep in mind too that the total effect of one variable on another variable is basically computed by summing up the indirect effect of that variable on the outcome variable and the any direct effects. So and so when we look at our output file, you can see, again, we have total effects. These are unstandardized. These are the standardized total effects. The direct effects, unstandardized and standardized, these are basically going to be the same values that you see in the original regression weight table. But again, if you want the bootstrapped test of significance, then you can just click on whatever effect and then go down to the bias corrected percentile method, and you can basically use either the confidence interval strategy or just looking at p-values in this little table down here.